Okay, so our speaker today is Francesco Pagliuca, and his title, as you can see there, is Equivariant Periodic Cyclic Homology for Ample Groupoids. Please, Francesco, go ahead.
Thank you so much for inviting me and giving me the opportunity to give this talk. As said, today we'll talk, this is part of my PhD project at the University of Glasgow, and it's a joint work with my supervisor, Christian Boyd. As said, today I will talk you about equivariant periodic cyclic homology for ample groupoids. So let's start with an overview of this talk. So the main setting for today will be this. So we will work with an ample locally compact house of groupoid and with A and B algebras with a certain action of the groupoid on them. And we will, in the first part of the talk, we will basically explain what these things mean. So the goal will be to define an equivariant version of the periodic cyclic homology, a bivariant equivariant version of the periodic cyclic homology for the algebras A and B. And this should be like an homology, so it should capture homological information about the action on these algebras. And so we will start reviewing a bit of, just saying a bit of history of about cyclic homology. Then we will introduce the main category in which we will work today. That's the category of G-modules. Then we will give the definition of the main definition of today. And finally, we'll discuss, hopefully in details, some of the results and properties we will get. Okay, so the first step towards what we are doing is for sure has been started by Oshel in 1945 with the Oshel homology for algebras, for standard algebras. Then in the 80s, independently from by Kohn and Ziegen, has been introduced a cyclic homology, and is one of its variants, the periodic cyclic homology. And the main goal to introduce this, at least for Kohn, was to find an invariant in the non-commutative framework, similar to what the Rham cohomology was for the commutative case. And this has been achieved in the following theorem, in which we can see there is this link between the periodic cyclic homology of the Frege algebra of a smooth manifold, and on the other side we have the Rham cohomology of the smooth manifold M. Okay, 10 years later after this, in order to prove excision, Cuntz and Quillen introduced the bivariant theory for periodic cyclic homology. And basically, this is what we will follow today. So we will follow this approach, so the bivariant approach. We will explain also why we will follow the bivariant approach. And we will talk more about excision when we will state right at the end of the talk. Finally, in 2003, Boyd introduced an equivariant, extended this to the equivariant realm. So for this theory for the action of groups. And what we want to do today is to go beyond this picture and define for groupoids. So extend from group to basically groupoids. Okay, so as I said, it's important, since we are following this approach, it's important to review quickly which is the Cuntz-Quillen bivariant approach for periodic cyclic homology. Okay, so we start with an algebra A. So here we are just considering the algebraic framework, so without any further structure on the algebra. So we'll consider this algebra A and its unitarization A plus. And then we will work with the non-commutative differential forms, which are defined as the tensor product of the unitarization of A times the n-fold tensor product of A by itself. And this will give us the n non-commutative differential forms, while the zero differential forms are given just by the algebra A. One of the main objects in the theory in this theory is given by the X complex of the algebra. Well, when the X complex is given by a super complex, so it's defined by these two objects, omega 0 of A and omega 1, the quotient of omega 1, with these two maps, the partial 0 and partial 1 going forth and back. At this point, if you know how cyclic homology is constructed, so which is the bicomplex that we use to define cyclic homology, you can recognize here that the X complex is like a truncation of the B complex that defines the cyclic homology, just at the first level, basically. So we have this bicomplex, we just cut over one of the corners, and then we get the X complex. And there is a geometric reason to do this. So the main reason is that we will consider algebras that are, Kuntz and Quillen considered algebras that were quasi-free. And so these quasi-free algebras have homological information just at the first, in dimension 1, say. So everything was above that they gave no homological information. And so they just focused on this X complex. And from this, we're also able to recover the entire cyclic homology. Okay, this was just more historical than other. And this partial 0 and partial 1 are basically the Hochschild boundary and the cone boundary. Okay, and so we say this is a supercomplex, where a supercomplex is nothing more than just a Z2 graded vector space, such that it squares to 0. So also where the usual differential squares to 0. Okay. And having this in mind, we can give the main definition. So the bivariant periodic cyclic homology defined by Kuntz and Quillen for the algebras A and B are given by this formula here. So here there are several levels. So we start from A and B, the algebras. Then we take the periodic tensor algebra of A and B. Periodic tensor algebra is just a sort of a limit of the usual tensor algebra. In this talk, I don't want to say more than that, because otherwise things get more and more complicated. So let's just think about as just a limit of the usual tensor algebra. Then we take the X complex of this tensor algebra, and then we pass to the Hom complex. So basically, we consider all the linear maps between these two complexes. And this defines a Hom complex where the differential is given by this formula, where partial A and partial B are the maps inside of the X complexes. And then we take the homology of this, because now this gives a complex. We take the homology, and this is the periodic cyclic homology of A and B, the bivariant version. Of course, from this, if you take A and B, just the complex number, you recover the usual periodic cyclic homology of A or the cohomology for both. Okay, now I know that most of you are fine with groupoids, so I just prepared a couple of slides and I will go super fast on this, but just to be sure that we are on the same page. So today we want, of course, what we want to do, all the construction we want to do involves groupoid. So a groupoid, the quick definition is just a small category where all the morphisms are invertible. Just to have a better intuition about this, we can consider as a set where we have a partial multiplication, a partial associative multiplication on a subset of the Cartesian product. Also this G2 that just gives us the maps that can be composed. Then there is an inversion that is also involutive, and multiplication, so composition and involution and inversion works well together. So there is some compatibility between the two. And of course, we can also think as a sort of generalized group in which we have more than one identity. So we have a set of identities that we will denote by G0 and can be thought as the object of the category if we consider the first picture. Otherwise, the idempotent arrows that coincide with their inverse if we think about the second picture. Again, we have the source and the range map, the usual source and range map. And But we are interested in topological groupoids. So we want to put a topology on this. In particular, we want to consider a locally compact and Hausdorff. We want to consider locally compact and Hausdorff groupoids. In particular, we say that a groupoid is étal if the range map, or equivalently the source map, is a local homomorphism. Something that we will use a lot is an open bisection. So an open bisection is just a subset of the groupoid, such that the restriction of the range and the source map to this subset are homomorphisms. And finally, as I said, we will focus on ample groupoids. So an ample groupoid is a groupoid in which the set of all the open and compact bisection forms a basis for the topology. Another equivariant characterization that is also very useful in the application is that an ample groupoid has a totally disconnected base space, and this also is very used in the theory. Okay, so this is the setting now. So we have our groupoid, ample, locally compact, and Hausdorff, and with the G0, it's base space. Now we can start constructing all the objects that we need just to give the definition. So first of all, let us consider the algebra of locally constant and compactly supported function from G to C. This, as a vector space, is defined as the set of this function, and this can become an algebra in several ways. So one way is with pointwise multiplication, the usual pointwise multiplication, and the other way is by convolution, where convolution is defined in this way. It's the usual convolution that we have for function. So, as I said, we have these two operations. In order to distinguish the vector space with one operation, the vector space when we add the other operation, we introduce another symbol. So we call, first of all, we call the algebra cis infinity of G with convolution product, the Steinberg algebra of the groupoid. And we denote this, so, I mean, this is the Steinberg algebra of the groupoid, and we denote this by dg. So when we see dg, basically means...
Sorry.
Yes.
So for you, C infinity doesn't have to do with any derivatives or something, in the sense of C infinity functions, I mean.
Yeah, actually here, since the base space is totally disconnected, smooth functions are kind of locally constant functions. If you...
Okay, and so these functions, these are functions to C. Okay, fine.
Okay. And so dg will be the Steinberg algebra of the groupoid. Okay, then we will consider modules over the algebra dg, and in particular we will consider essential modules. So a module is essential if these isomorphism hold, so that we can recover basically M from the tensor product of the M by dg over dg. Okay, and the category we are interested in, so the category of G modules, is the category of essential DG modules with DG linear maps. Okay, and we will call and denote this category by G mod. Okay, now that we have the main objects we want to work on, we will give an alternative picture for these objects. Why we do this? First of all, it will give us a better understanding of these objects. First of all, it allows us to prove some properties in a faster way, probably. And also, I think it's pretty interesting to have a different picture for G models. So first of all, remember that CC infinity of G becomes an essential CC infinity G0 module, so on the function on the base space, via the pullback of the range or the source map and the pointwise multiplication. So we pull back the function, so it's now a function cc infinity of g, and then we do the pointwise multiplication. This justifies this notation, in which we have cc infinity of g tensor cc infinity of g with this decoration R and A and S, and this is the balanced tensor product over cc infinity of g0 with respect to the module cc infinity g0 module structure I just defined. So with the pullback of the range or the source map and the pointwise multiplication. Well, then we consider this homomorphism between these two spaces, G SRG and GRRG. These two are basically the spaces of all the function with the same source and range, and the function, the arrows with the same source and range, and the arrows with the same range. So these two spaces are homomorphic, and this homomorphism induces a cis infinity G linear homomorphism at the level of the function. So just by transposition and identifying the cis infinity of G times G with cis infinity of G tensor cis infinity of G. So using this identification that we have, we can induce this the linear this isomorphism between these two spaces. Okay. Then we also introduce these maps, D0, D1, and D2, from the composable arrows to G. And basically, these are just the projection on the second, the composition, the projection on the first, for all the composable maps. Then we compose these maps with the range and the source. Then we obtain this V0, V1, and V2. And then we have these three maps. Now, these three maps that basically just so we have composable arrows, G, and then we take the three arrows, alpha, beta, and gamma, and then we compose just the last one by the second in the first, then we compose by the composition of the first and the second with the third, and then just the first one. So these three arrows, when we gives us just the right meaning of being an action, so that if we compose by the first, then we compose by the second, it's the same thing that composing by the composition. And this at the level of the functions. So again, when we consider the transpose at the level of the function, we gives us a coaction identity that we will denote in this way. So when we see this D0 star is just the transposition of the first map at the level of the function.
Okay,
so this.
So you mean
Yes.
that your CC infinity of G is a bialgebra?
Is it?
Bialgebra? So you just define a co-multiplication on the functions, right? Because when you take star, I understand you are taking, so these are the maps induced at the level of functions, aren't they?
Yes. Yes.
So are you claiming that that essentially that the product of the groupoid induces a co-multiplication on your algebra functions?
Yes, I think we can rephrase in this way. Yeah, I don't know too much about the specific words we are using, but I suppose yes. So basically, you just pass at the function, you do the identification I said before, so just breaking the times and replace with the tensors, and then you substitute with the convolution, basically. So yes. So we have this identity here. This identity gives us the following definition. So we want to define this CC infinity of G comodule, and this terminology is taken by the quantum groups, and is an essential CC infinity G0 module M. So we take our module over the base space. So basically, if we think about the discrete case, for example, we are just taking a vibration in a sense. So we have all these fibers, and then we have this essential module, with a cis infinity G linear isomorphism, this Tm, that gives us the information about the action, so what is happening, that satisfies the coaction identity. And here, this coaction identity ensures us that we are considering a true action. Okay, so this comodule is given by these two information. So the module over cis infinity of G0 and this linear isomorphism that has this property that follows this identity here. Okay, and a morphism of cis infinity G comodule is just a cis infinity G0 linear map that commutes with the maps Tm and Tn, where now we can call this map a canonical map for M. Okay, so now we have this picture of so we have the picture for G modules, and now we have the picture for cis infinity G comodules. What we want to show now is that these two pictures actually agrees. So that basically we are considered the same objects. Okay, so we will show how to pass from a G module M to a cis infinity G comodule. So let's start with the G module M. This is automatically an essential cis infinity G0 module with the action given by just restricting the action. So just given by the inclusion of G0 in G. And then using the identification, this isomorphism here, that comes from the fact that M is essential as a G module, then we obtain this commutative diagram. And this chasing this diagram, we obtain this map Tm that turns our module, our G module, in a cis infinity G comodule. This procedure gives us a functor. So it's a functor from the category of G modules to the category of cis infinity G comodules. And turns out that this functor is an isomorphism of categories. So it's an isomorphism between the category of G modules and cis infinity of G modules. So these two pictures actually agrees. So we have just a different ways of looking at G modules using this other picture. Okay, and this allows us to prove some interesting properties. First of all, we can show that if we have two G modules M and N, and we take the tensor product of these two G modules, the tensor product, the balanced tensor product over cis infinity of G0 is again a G module. So we can define an action on this tensor product, and this action is the diagonal action. But it's the diagonal action when we consider open and compact bisection. So we have a nice formula when we consider an open and compact bisection of the groupoid that recall us as the diagonal action of the usual. Okay, and this is just saying that the category of G modules with this tensor product is a monoidal category. So we have this multiplication operation in which the unit is given by the function on the base space. So G mod with the tensor product with cis infinity of G0 is a monoidal category. And as said, we are interested in algebras with these actions. So we want to consider algebras. So a G algebra is a G module A with a multiplication. So an associative multiplication that is also DG linear. Okay, another way of rephrasing this, if you really like a category theory, is that we are considering a monoid in the monoidal algebra that we have defined. Okay, let us now give some examples of G algebras, and these examples will be ad hoc examples in the sense that we will use in a moment also for the main definition. So the first and simplest example of these algebras is given by the function on a totally disconnected and locally compact G space. So we take X. We have the groupoid action of our groupoid on X, so with the anchor map and the action map. Then this turns cis infinity of G in a G algebra with the pointwise multiplication. In the same flavor, we can consider as G set the set of loops in our groupoids. So we consider all the loops of our groupoid, the isotopy group, the set, all the arrows with the same source and range with the adjoint action. We consider the cis infinity function of this space, again with the pointwise multiplication, and this is again a G-algebra for what we said right now. And we will denote this as OG. Then if we consider a G module E, we can take the tensor product of the G module by itself, and we can consider a DG linear map from this tensor product to cis infinity of G0. This is a G-algebra with the multiplication defined by this formula. And this is the analogous of the finite rank operators for an usual Hilbert module, for example. Okay, in particular, if we take a special G module, so if we take the E as dg, and the bilinear map given by this formula here, so we are just summing all the function evaluated at the same arrows ending in x. Well, this deserves a special name, so we will call this kg. And this again is algebra. Finally, the last example I want to give is the crossed product. So in analogy for what we can do for discrete groups, also here we can consider the crossed product of a G algebra A by a groupoid G. So this is defined as the tensor product of A by dg, and there is this multiplication that is the usual twisted multiplication. Yes.
Sorry, so is there a special choice of A, maybe CC infinity of Z0, for which you recall your A of Z is D of Z?
For which you call your A of G D of G.
Yeah, so this A, the Pascal A, I suppose it represents the Roman A.
Yes.
Okay, so if Roman A is the ring over which you are tensoring,
yes,
then I guess you recover the G.
Yes, because you can absorb, the tensor product is balanced over cis infinity of G0, so you should absorb.
So the G should be curly K of G. Because A cross product G is curly A G. So I'm just pointing out that the notation can be a little inconsistent because the Pascal A of G doesn't have any Roman A in it. However, the definition depends on the Roman A. And if you your A correctly, you get the G.
I see your point, and you are totally right. And I will show you in a second why I was wrong in the sense that I put this name here, but sorry about that. So this construction is just for general A and G. And in the case in which we have A OG, we call this crossed product curly A of G. Okay, I hope now we are fine. Right? Okay, I suppose, yes.
Yeah, okay.
Okay, sorry, yeah.
I got confused myself to this one.
Okay, so so we have also this special GeoAlgebra here. Well, Now we are ready to introduce another category of modules we will use often. So it's the category of G anti-Jeter different modules. So a G anti-Jeter different module is an essential module over the algebra A of G. Well, what we want to do is to consider, when we consider an anti-Jeter different module, is to consider something that is at the same time a G module and is also a OG module structure, where this OG module structure is compatible with DG, so it's DG linear basically. The only example we will give about G anti-Jeter different modules is this one. So when we take a G module M and we tensor with OG, we obtain an anti-Jeter different module with the diagonal action on the G action is given by the diagonal action. The OG action is given by the pointwise multiplication on the first vector. Okay. Well, now we show that we can associate canonical maps, certain canonical maps to with G anti-Jeter different modules in the following way. So we start with this map that is similar to the map we have seen also before, and this turns out is an automorphism of AG bimodules. So from this, again, in the same flavor of the construction we have done before, we can construct this diagram. This diagram is commutative. And from this, chasing the diagram, we can define the map Tm, where Tm is just an automorphism now from M to M, such that it commutes with all the G anti-Jeter Drinfeld maps of G with the morphisms of G anti-Jeter Drinfeld modules. So basically, we have this equality here, where phi is the morphism I was saying, and so this map is canonical and is associated to the module M, or we are considering at the beginning. Well, this brings us to the definition of paracomplexes. So a paracomplex, in this case, we were considering super paracomplexes, so say again with the same Z2 grading, is a supercomplex together with an invertible morphism, so this automorphism from the object to itself, such that it has a special property. So it's not anymore a complex, so it doesn't square to zero. But the fact that this doesn't square to zero is, in a sense, controlled. So controlled by the morphism, the canonical morphism we associate to this. The differential, the squared, is not zero, but is the identity minus this map. So this is now a paracomplex. And of course, for what we just constructed, we can say that in the category of G anti-Jeter different modules, we can consider naturally paracomplexes. And this will be crucial in the definition we will give in a second for the homology we are considering. Okay, so now that we have done all the preparation in this case for the main definition, we are ready to give the definition. So we consider A and B G algebras. Then the bivariant equivariant periodic cyclic homology of A and B is defined by this formula. So here there are again several even more levels of complexity. So again, we start with A and B. First of all, we take the tensor product with the curly K of G, the algebra we have defined before, that is associated to the linear pairing of dg times itself to C infinity of G0. Then we take the periodic tensor algebra, and now is an adapted version of the periodic tensor algebra Cuntz-Quillen considered. Then we take the X complex of this. Now it's not just the X complex, because you can see there is a little g as decoration, so it's an equivariant version of the X complex. So this now is defined in this way. So the two objects that we have are omega 0 of A, but now these are not anymore just non-commutative differential forms, but are equivariant non-commutative differential forms, defined now in this way. So we basically take the n tensor product of A by itself, then we tensor with the unitarization, and again we tensor with OG. And so this now gives the n non-commutative differential forms. Okay, and there's just one crucial point here, is that now what we call the X complex is not anymore a complex, because now, as you can see, is a paracomplex. So it means that it does not, the maps, the differential in this complex does not square anymore to 0. And this is can be a problem, but is easily solved in our case. Because now what we can see is that omega n of G is now a G anti-heterodimmer module. So because what we have done here, we took omega n of G0, that is a G module, we tensored with omega G, and this, from the example I gave before, is basically the only example we care about in this talk. And so basically gives a G anti-heterodimmer modules. So there is a canonical map associated to this, and this canonical map controls the fact that the square of partial A and partial B are different from 0. So basically, when we pass to the Hom complex, we obtain a true complex. So here, the solution to the fact that we are not considering a complex but just a paracomplex is to pass directly to the Hom complex. And so from the very beginning here, we consider the bivariant approach of Cuntz-Quillen that automatically, in this case, solves the problem, once we are sure that these properties work. And so here, the square of this partial, so the differential of the Hom complex, is again 0. So it's a true complex. We can take the homology, and this gives the periodic cyclic homology of A and B. Just another point to outline is that here we are considering the AG linear function of, so the Hom complex is on the AG linear functions, not just linear function or DG linear function, because we want to control also what happens to OG. Okay, now we can discuss some of the results and properties of this homology. Let's start with a special case, so when the groupoid is discrete. So if we have a discrete groupoid and we have A and B G algebras, then we have this canonical isomorphism that connects basically the periodic cyclic homology of A and B to the periodic cyclic homology of the localization of A and the localization of B at X. And now this is equivariant respect to not the groupoid, but the isotopy group in X. So let's explain better this. So we start with our groupoid. We can decompose this. So the groupoid acts on the base space. So it means that we can decompose the base space in orbits. Per each orbit, we take a representative of this orbit. And for each representative, we can consider the isotopy group. So the fact that we can write the base space as as disjoint union of orbits give us this direct sum decomposition. And in each orbit, so when we are considering just a transitive groupoid, we have a sort of Morita equivalence for this. And so we can consider, we can localize in a sense to the orbit, to the isotopy group there. And so for each G anti-heterodimmer module M, we can associate a localized version of this module. Then what we do is to apply this functor here to the Hom complex. verify the compatibility with the boundary maps, so delta 0 and delta 1 we have seen before, and then we recover the result for the discrete case here. Okay. Also, another here now there are three properties that connect the periodic cyclic homology with KK theory. And in particular, the first one we are considering is the homotopy invariance. So just a few definitions. So if we start with the G algebra A, we can define the G algebra A01 as the tensor product of A by the smooth function on the interval 0, 1. Here we just notice that the tensor product is over C, so it's just the usual tensor product, and the G action here looks just at the first element, so just A. So it treats like the second element as like a dummy element. So it's just on the first. And then we define a smooth G-equivariant homotopy between homomorphisms of G-algebras, a G-equivariant homomorphism of G-algebras, as a G-equivariant algebra homomorphism, capital F, from A to B of 0, 1. And we say that this is a smooth homotopy if when we evaluate at the 0 and 1, we recover phi 0 and phi 1. Okay. Another remark we should do is that every G-equivariant algebra homomorphism, so if we take our G algebra A and B, we take a G-equivariant algebra homomorphism between these two, this homomorphism induces an element, so a class in HPG0 of AB. This is just by considering the lifting at the level of the tensor algebra, the X complex, and then taking the homology. So it's just a class inside there. So the first theorem is that if we have A and B G algebras, and we consider a smooth G-equivariant homotopy from A to B of 0, 1, then the element induced by phi 0 and phi 1, so when we evaluate at the beginning at the end of this segment, are the same in HPG of A and B. So, and this is the kind of usual homotopy invariance for homology theories. The second, just a few words about the proof of this. Well, the proof of this follows quite closely the proof for the group case. So basically, we just had to adapt some of the objects, but more or less was similar. So there's not too much to say about this. What is more interesting is the stability. So stability means that we have our homology, bivariant homology for A and B, and we want to be sure that it absorbs the algebra associated to a bilinear map from E to E. So we have E a G mod, we equipped with the surjective G equivariant bilinear map pairing.
Wait.
Yes.
So can CC infinity of Z0 not be projective as an essential module over itself? You say if that and E are projective.
Yes, cannot be.
Because you're imposing a condition not only on E, but also on projectivity of CC infinity of Z0, I would assume.
Yes.
But this is projective over itself always, isn't it?
No, it's not. Let me think about an example. Okay, now maybe it's better if we, yeah, we'll think about this just a moment, and I
Okay,
will
sure.
tell you later. Yeah. So assume that also CC infinity of G0 and E are projective of as essential CC infinity of G0 modules. Then we have these natural isomorphisms. So basically we are saying that HPG of A tensor K of E B is isomorphic to just HPG of AB, and the same is also true on the second entry. Okay, and this is true for all the algebras in. So now the proof of this. First of all, we have a simple case. Let's say not simple case, probably bad word, but we have a case in which we know more or less what to do, in the sense that the proof of this case that we call the admissible case follows what has been done for the group case. So in the admissible case means when there is an embedding of CC infinity of G0 in E. So there is a G-equivariant linear embedding of CC infinity of G0 in E that respects the restriction, that respects the bilinear pairing, in the sense that the bilinear pairing restricted to CC infinity of G, CC infinity of G just agrees with the pointwise multiplication. In this case, we follow the same approach of the group case. Then the problem for the general case is related to this projectiveness, because the fact that we assume that E and CC infinity of G0 are projective as CC infinity of G0 modules ensures that there is this isomorphism here. This isomorphism from G tensor E direct sum kappa, where now this kappa is an infinite cardinal such that E admits a generating set of a cardinality at most k. Okay, so projectiveness give us ensures that we can embed one in the other, in a sense. And when we consider infinitely many copies of this gives this isomorphism. And this isomorphism is at the level of G modules, so not just at the level of CC infinity G0 modules. Okay, and using this isomorphism and playing a bit around with the infinite sums, we are able to prove that the X complex of the tensor algebra of A tensor Kg is the same thing that is a homotopic to the X complex of the tensor algebra of A, in which we first tensor it with the Kg and then again with the key E. So basically it absorbs the tensor of key. In here, the main points to outline is that we are basically using this isomorphism that we defined before, and we are also using the fact that the action on CC infinity of G0, the infinite direct sum of CC infinity G0 by itself, is admissible. So the linear pairing on this infinite sum is admissible. So basically, we are using two things: the isomorphism that we have here and the admissibility for the case of CC infinity of G0. And this gives us the result. Okay, another consideration in the case in which E is just dg, we are just saying that tensoring with kg once or tensoring with kg infinitely many times is basically the same. A corollary of this, okay, so we can say something stronger in the case in which G is a proper ample groupoid, and the quotient of the base space is paracompact. So just a couple of words about the assumption that we have here. So properness and paracompactness. Oh, okay. Properness and paracompactness together ensures that there is a cutoff function for this groupoid. And the use of this cutoff function is essential for this construction. So basically means this cutoff function in this case has also special properties because it's again a locally constant function. So again here, the use of this cutoff function just ensures us that we can lift maps from at the level of CC infinity of G0, so CC infinity G0 linear maps to G equivariant linear maps. And the construction of this is quite technical, but using this cutoff function, we can, and doing the sort of averaging procedure, we can pass from, we can lift the linearity. Then we observe that CC infinity of G0, in this case, is a direct summand of dg, as in the category of G modules. Of course, this is always true in the category of CC infinity G0 modules. And the maps that we use are the integration map and the inclusion map, where the integration map is the map that goes from dg to CC infinity of G0, take a function, and just you pick a point and you do the sum of all of the function f, evaluating or at all the arrows that ends in that point. So, and we call this map the integration map. The integration map is always a G-linear map. The inclusion map is not. So what we do is using this averaging construction to lift the linearity of the inclusion map from CC infinity of G0 to dg, dg equivalent linear maps. And this gives us the fact that now CC infinity G0 can be seen as a direct summand of dg as G module. And this gives now with this we are in the admissible case, and so it gives the result. Okay, excision is the last property that link, in a sense, KK theory and equivalent periodic cyclic homology. So I said something at the beginning. So this was one of the missing properties that Cuntz-Quillen were trying to prove when they introduced the bivariant theory. And excision is the existence of these two 6 terms exact sequences given by induced by an extension of G algebras. We can see here at the beginning from K, E, and Q with the CC infinity G0 linear splitting. The proof of this theorem again follows as expected the proof of the group case. Here the point to outline is that this is really an important theorem, and the main work for this has been done in the series of paper of Cuntz-Quillen. From that original idea, with some adaptation, we get also this result in the equivariant in the equivariant case. So I will not spend too much on this. And finally, we got a result on of the so-called Green-Julg theorem. So basically, this result has been stated by two in 1999 about KK theory. And now since there is this sort of correspondence between these two theories, so equivalent periodic and KK theory, and also in the equivalent case, we add a sort of analogous of the KK theory 1 in periodic cyclic homology. And here, again, we are assuming that our groupoid is proper, and the quotient of the base space is paracompact. With this assumption again, so again, we work with the cutoff function and this kind of technique. We are able to prove that there is a natural isomorphism between the periodic cyclic homology of CC infinity of G0 and A with the relative version of the periodic cyclic homology restricted to CC infinity of G0 and the crossed product of A and G. where A is just a G algebra. So here, just a few words about the notation. When you see HP of CC infinity of G over G0, just means that we are considering the equivalent periodic cyclic homology associated with the quotient of G0 by G, that is again totally disconnected and Hausdorff, viewed as as an ample groupoid again. So restricted to this. So all the construction we are doing are relative to this ample groupoid now. So the techniques used in here are basically localization techniques. So we localize at elements at the orbits of our groupoid, of our base space. Then we prove a localized version of the theorem. So in which we basically localize everything to these orbits. And so once we were able to prove this localized version with a local to global procedure, we are able also to prove the general statement. And to prove the localized version, basically, what we do is try to reduce everything to the case of finite groups. So basically, we observe that with the assumption that we have, so that the groupoid is proper and G over G0 is paracompact, we obtain that the isotopy group of G of XX, in which we consider the orbit, is a discrete group. And so G of XX is a finite group. So with a bit of computation of these two sides of this, we are able to reduce to the group case, and the group case has been already proved by Voigt at the beginning of the 20s. And so we got the result also for this. Okay, I think I've done, I hope, in time. Thank you so much for the attention. And
Okay, so thank you very much for your nice talk. I have a couple questions. So there is this theorem in bivariant K theory that when you have equivariant bivariant K theory, when you take it over a finite group, then there is an adjunction between so you have on one side the category of G algebras, and on the other side the category of algebras, and you can go from G algebras to algebras from algebras to G algebras by taking the trivial action, and you can go the other way by taking the cross product, and the theorem says that these two functors are adjoint. So you get a formula. It has somebody's name. I don't recall the name of it.
Isn't that Green-Julg?
Sorry?
Isn't that also called Green-Julg?
Green-Julg, yeah, the Green-Julg theorem. So is this Is this theorem D the version of that?
Yes, it's exactly that. So for the usual periodic cyclic homology, you will have HP of C, A, and then, the equivariant. So HPG of C, A, and then on the other side, we'll have HP without any decoration of C and the cross product of A, G. So it's basically what you said, I suppose.
Yeah, but in the Green-Julg, so it's bivariant. So you do not have to fix. Yeah, there is an A and a B.
I see. This
also
is
Green-Julg is slightly stronger than this version. I think that one really comes down from that adjunction at the level of bivariant K theory.
Okay,
this
yeah,
cross
because
product and the induction functor.
I see, because in the group case, there's this version here, and there is also the dual of this, which you basically consider the other one. I think that we are just able to recover this version here. Not complete. I mean, now I don't want to say stupid things, but I don't think we can recover also the other in a immediate way. Yeah, I don't want to say wrong things, so. Yeah. But yes, I mean, it's that tune there.
Okay. So the fact that you call the Steinberg algebra the level value calls AG or KG, CC infinity of G, seems to indicate that you are aiming, you're regarding this as the algebra of smooth elements in the sister algebra of the groupoid. And so that this means that perhaps your thesis project includes considering sister algebras, groupoid sister algebras, and perhaps a version of local cyclic homology or something.
Actually, no. For what was my background, we decided to work more on the just algebraic framework.
Yeah,
And
but
just to
okay,
I mean, I
but if
think
you
the CC infinity notation might come from taking smooth functions on totally disconnected Lie groups. So in that case, they just coincide with locally constant functions.
yeah, okay, but what I'm aiming at is that if you only care about the pure algebra case, you just need a field of characteristic 0,
Yeah.
and for homotopies, you just take polynomial homotopies. And I suppose you can do everything in that setting, right? Because you're not, if your functions, the fact that your functions are C infinity ends up meaning that they are locally constant, then that is the same as saying that you are taking the continuous functions, whereas in the field you put the discrete topology.
discrete topology, yes.
So you can do that with any field with a discrete topology, and for purposes of proving excision and homotopy invariance
Homotopy, yeah.
and averaging kind of things, unique characteristic 0.
Yes,
So
you need that there is at least Q involved, I mean, contained in, because you want at a certain point,
yeah,
in particular, I think it's in the homotopy that there is the problem in which you want to consider derivatives at a certain point. So you need there.
yeah. So
Or the
with a
integration
field
part,
of
yeah.
characteristic 0, yeah. Yeah. So my only other observation is that I've been reading several papers on Steinberg algebras, and even if the notations, there are some variations, but they are different from what you write. Nobody writes DG or what you call for the Steinberg algebra.
They usually, yeah, they
Either
use.
AG or KG or AKG. Yeah.
Did you get it from one of Ralph Meyer's papers?
Yeah, I think we are using that kind of.
Mhm.
I see. Yeah.
That's the network. So
Yeah,
I
you're
mean.
contaminated by that. Okay. So does anyway one in the audience have other questions?
You stole most of my questions and now have to leave.
Oh, okay. Well, I'm sorry. Okay. So I'll stop the recording now.